grade math students. This is an OAA review for both honors algebra and pre-algebra. You know you're going to take the same test, so you may watch the same review videos. All right, the test is Thursday, and I'm expecting you guys to give me your best effort. Not just me, but you, your best effort, because you deserve it. All right, we're going to start with the number systems. Remember, we did Venn diagrams to help us remember. If I were you, I'd practice this Venn diagram so that you could repeat it when you first get to the test. You could write it down really quick right at the start of the test and use it whenever you need to. Remember, in this most inside circle, we have the natural numbers. And the natural numbers start with 1, and they continue on forever, only counting whole numbers, no fractions, no decimals, no negatives. Then, after the naturals, we had the whole, which was a W, right? And whole numbers. So maybe I can write it down here. All right, W stands for whole numbers. And the whole numbers are just like the naturals, except they have 0 in them. They go 0, 1, 2, 3, and they go on forever. No fractions, no decimals, no negatives. All right, then the next one we had were the integers. Right, Z was the integers. Okay, and the integers are the ones I like to think of as a number line. Now, a lot of you make this mistake, and I hope you're listening closely. The integers do not include negative fractions. They only include the negatives of the whole numbers. They include whole numbers and the negatives. Notice I will not put negative 1/2 on this number line. Okay, not negative 2.3, not 5/6. Integers do not include fractions or decimals. No fractions or decimals. Right? Okay. Then we get to the rationals, which is Q. Q stands for rational. Rational. Okay. And this includes all fractions, decimals that end or repeat. That end or repeat. Okay, so this is where the negative fractions show up, like negative 1/2 belongs in here, 5 2/3 belongs in here, 6.4 repeating belongs in here, 2.3 belongs in here, negative 1.8 is rational. Okay, so are all the other numbers before it. 1 is rational, because if I'm here, if I put a little smiley face inside the natural circle, is that smiley face inside the whole circle? Sure it is. The whole circle goes around it. It's also inside the integer circle, and it's inside the rational circle. All right, now over here off to the side, we have some special numbers that are decimals that never end or never repeat, and these are your irrationals. Okay, so like pi is the most famous. It's 3.1415 and ... The square root of 2 is irrational. I showed some of you in class how the square root of 2 to 1,000,000 decimal places. Okay, it goes on forever without repeating. In fact, any non-perfect square you take the square root of is an irrational number. All right. If you see ... after a number, it could be a negative 6.1432 ... It means it goes on forever without repeating. Those are the irrationals. And altogether, they make up the real numbers. And I don't believe you're going to have to worry about anything except real numbers on the OAA. All right, so that's number systems. We'll review a little bit in class about those. I wanted to do patterns. Patterns is probably one of the most important things. If you get the number, say 4, 7, 10, 13, and 16. Some of you never mastered or have forgotten the technique I had for developing a pattern. Okay, I make a little table. I put in there, and I go 1, 2, 3, 4, 5. Now, almost everybody goes, hey, it's going up 3. But then what a lot of you do think it must be n plus 3. It is absolutely not n plus 3. If we're n plus 3, then every pattern that goes up by 3s, like 3, 6, 9, or 17, 20, 23, if it was as simple as you're making it, where you just say, well, it's just n plus 3 because it's going up 3 every time, then that would be true of this pattern, that would be true of this pattern, it would be true of millions and millions of patterns. You can't have one formula that generates millions and millions of different patterns. Each pattern has its own unique formula. So, what does it mean that it's going up plus 3 every time? Well, if it's going up plus 3 every time, that means the pattern is something like 3n. Now I'm going to plug in these black numbers in for n. I'm going to substitute them in, and I'm going to get 3, 6, 9, 12, and 15. And then I'm going to compare them. How do I turn 3 into 4? Well, I've got to add 1. How do I turn 6 into 7? I have to add 1. How do I turn 9 into 10? I'm going to add 1. How do I turn 12 into 13? I'm going to add 1. The formula must be 3n add 1, or 3n plus 1. Okay? One thing I want to point out here. 2, 4, 6, 8 is not every even number. It is not. Okay? If it were every even number, 0 would have to be listed, -2, -4, etc. Just because there's some even numbers there doesn't mean the formula is every even number. In fact, every even number is not a formula. It's a statement. All right. Now, remember that if the pattern goes like this, where we go, let's see here, 2, 5, 10, 17, and 26. Okay, you make your little table, right? 1, 2, 3, 4, 5, and n. And then you look and see, hey, this is plus 3, and this is plus 5, and this is plus 7, and this is plus 9. Oh, it's not the same amount every time. But if you go to the second level, plus 2, plus 2, plus 2, it is the same. When you have to go down 2 levels, that means your pattern is some type of n squared. So I'll plug 1, 2, 3, 4, and 5 in for n squared and get 1, get 4, get 9, 16, and 25. And then I'll see, how do I turn 25 into 26? I add 1. How do I turn 9 into 10? I add 1. 4 to 5, I add 1. So my formula is n squared plus 1. If I'd been subtracting 3 every time, then I would subtract 3. N squared minus 3. But in this case, I was adding 1 every time. Now, one thing, I hope you're really intelligent when you take this test. A lot of times they'll give you a question like this. They'll say, which expression could generate the following sequence of numbers. Okay, and they'll give you these numbers here. They'll give you, let's see here. Let's go 3, 8, 13, 18, and then they'll give you 23. Okay, and they'll have 4 choices. A lot of times these are multiple choice types questions. And the first choice will say n plus 5. The next one will say 5n. The next one will say 5n minus 2. And the next one will say something like not enough information. And I can't tell you not enough information is never the answer, but I can tell you kids pick it way too often. I would check 5, 6, 7 times before I would settle on not enough information. Because I know you guys in your past, you don't do it so much anymore, but in your past, if you didn't know the answer, obviously, then you went to the I don't know or you can't do a card. And that's just not the case. And I think a lot of you are learning that, you know, oh, I have to stop, I have to think, I have to plan something out, try an approach, maybe try a second or third approach, and then I usually come up with an answer. All right, now look, this is the first term, the second, the third, the fourth, the fifth. Those of you that think you want to pick A, put 1 in for N. Is 1 plus 5 3? Absolutely not. Then this cannot be the right answer. Let's go down to this one. Is 1 times 5 3? No. Then it's not the right answer. Okay? It is 5 times 1 minus 2 3. Yes, it is. That one checks. I'm going to check 3 or 4 before I settle on the answer. All right, 2. 5 times 2 is 10, minus 2 is 8. That one checks. 3. 5 times 3 is 15. 15 minus 2 is 13. That one checks. And I'll check one more just to be safe. 5 times 4 is 20. 20 minus 2 is 18. It checks. C is your answer. Notice I didn't actually create the pattern. I tested the patterns they gave me. Remember that in math, you should read your answers first and then go read the question. Okay, hold on one second. I wanted to talk really quickly about scientific notation because I know some of you get rusty on it. And your calculators will do scientific notation for you. I plan on showing you how to do that, all right? But first of all, let's take a standard notation number like 6,543,000. And also we'll take this number here. Format tenths, hundredths, thousandths, 10,000ths, 100,000ths, 125 100,000ths. And I'm going to convert them to scientific notation. Well, I always need my number in scientific notation to be between 1.0 and 9.99. All right, so I'm going to put my decimal point here. Okay, I need my number to be 6.543. Now, where was the decimal point in standard notation? Well, it was here. I'm going to see by how many times I divided by 10. 1, 2, 3, 4, 5, 6. So I'm going to have to multiply this by 10 to the 6th power. Okay, now with this number smaller than 1, I'm going to want my decimal to be right here, my decimal point. So I'll have 1.25, which is 1 25 hundredths. And the decimal point was right there. And in this case, I had to multiply by 10, by 100, by 1,000. So I'm going to multiply it by 10 to the negative third to undo the change. All right, I'm dividing by 1,000 here. That is scientific notation, standard form to scientific form. All right, let's look at this one here. Let's go with 4.423 hundredths times 10 to the 5th power and 4.205 times 10 to the negative third. Okay, so I'm going to take this 423, the decimal point was here, and I'm going to multiply it by 10 to the 5th. Well, 1, 2, 3, 4, 5, and I fill in my zeros. My new number is 423,000. And for this one, I've got to divide it by 10 to the negative third. Remember, a negative exponent means to use the stairs, so this is the same as 4.205 divided by 10 to the positive third, which means this number is going to get smaller. So I take the 4.205, but the decimal point goes the other direction. It goes 1, 2, 3. And so therefore the new number is 0.004205. All right, that's it for the first review video. Mr. Lawrence signing off. Have a good night, everybody.